Yeah, good morning. Yeah, thank you. Yeah, Brandon, for the introduction. So this is joint work with my former PhD student Jiacheng Li. So he graduated in January and joined the Pinked Interest, and he told me he cannot travel to present. So I'm here. So this work is about membership inference, which we have seen in a number of papers. So there are a couple of settings in membership inference attacks. So in the black box setting, the attacker only can query the model and then try to determine whether a particular instance is used in the training. So then in the white box setting, where the attacker have the model parameters, and then in the federated learning setting, the attacker is basically the server who can see the gradient update during the training. So therefore, that's the most powerful model in the membership inference attack. So in this paper, we deal with black box membership inference attack. But the initial idea of the paper came up when my student and we were working on his previous paper, which is membership inference attack in the federated learning setting. So we developed a new attack in the federated learning setting, and then we need to compare with the baselines. So we evaluated the black box attack in the federated learning setting, and then to our surprise, we find that the membership inference attack become much less effective. The black box membership attack become much less effective when the model is trained in a federated learning setting. So at that time, we were first try to finish that paper, so we kind of just put this on hold. And then after that paper was published in iClear last year, so then we returned to this problem. So basically, what we observe is that for the same training data set, if you train the model in the federated learning setting, then it's less vulnerable to black box membership inference attack. So basically the main difference is in the standard training, you go through all the data like one by one. In the federated learning setting, the data is divided into different subsets. And then you do this in iteration. In each iteration, you train on each subset significant more steps. And then you average the result, and then you merge the model. So somehow that process makes the model less vulnerable to membership inference attack. Yeah, so to illustrate the training process, so essentially the data is divided into different partitions, and then we train on each partition a number of steps, and then we will aggregate the model, and then this will iterate. So we talked with Bruno about this finding that if you train it this way, it's less vulnerable. Then Bruno said, oh, this is, there's actually a name for this training. I guess some propose this, where's the name on here? So anyway, so this is being studied. So then this slide summarizes the effect we observed. So here, the blue line is the training accuracy. The kind of reddish line is the test accuracy. So basically, we want the gap between the two lines to close. If it closes, it means that it's less overfitting, so therefore less vulnerable to membership inference attack. And the x-axis is number of virtual clients. So essentially, even if we are not in the federated learning setting, we can separate the data into subset and then train them in a virtual federated learning setting. And the green line is the attack accuracy, so the AUC of the black box membership attack. So this is the effect, and then so that's the first idea, the known as subspace training. So then we try to see whether we can improve further. So the idea we came up with is can we simulate essentially differential privacy? So there's this concept called counterfactual data set, which is a real data set except you change it somehow. And in this particular case, the counterfactual data set we consider is essentially remove one data point. So, and the counterfactual invariance means that what the effect is equivalent to the case of before making this change. So if we achieve this kind of counterfactual invariance, then basically we are membership invariant. So then we should theoretically remove a membership inference attack. So, but you can't actually train the membership invariance classifiers. It's very, very expensive. So we need faster approximations. So what we came up with is we train in this virtualized federated learning style. So we divide the data into multiple data sets. And then in each epoch, after we get the model back, we had additional step to train each submodel. So before merging them, we train each submodel to reduce the following loss. So what this loss does is for every data set in this particular submodel, we want to calculate the distance of the loss of this submodel and the average of all the other model on this instance. So the intuition is if this instance is very special and when we train on it, the loss reduced dramatically in this submodel, all the other submodels are trained with data not including this instance, so their loss will not be as low. So then by making this loss difference small, we are basically reducing the impact of this instance on the on training. So therefore, we are making the membership inference attack on this instance less effective. So that's the essence of this idea. So this is kind of documenting the algorithm. So I guess just to make it clear, so the training data is divided into capital C partitions. So we on each iteration, we will first train on each of the subset doing the standard kind of a couple of epoch of SGD training. And then we do update to reduce this cross difference loss that are showing on the previous slide. And then we aggregate the model and then we repeat. Yeah, so basically the update part is just to do gradient update to reduce this cross difference loss. So then to evaluate, we evaluated a number of the attacks that we find were state of art at the time we were doing the evaluation. And we also compared with a number of defenses that we consider to be state of art. So here I just want to briefly summarize two of the newer defenses. So the Selena defense, so this was I think published 2 years ago in USENIX Security. So the idea is there's similarity with our idea. So you train multiple models. You first train multiple models. Each of the model is trained only with 60% of the training data. And after you train this, for example, 20 different models, each with 60% of data, then you train a new model. But the model training is used distilled input where the label for each training instance is given by this 20 model instead of the original label, and it's a soft label. And for each instance, the label is the average prediction of the models that are trained without it. So on average, for every instance, there will be, I guess, about 40% of the models. So out of 20, that will be like 8 models that are trained without this instance. So then we'll average those models' output and use that as a label to train the instance. So again, this is trying to train a model with a label that are kind of not affected by training with that instance. So this is the intuition that's similar to our idea. So this slide shows the main comparison result. So the x-axis is testing accuracy, and the y-axis is the attack accuracy. So ideally, we want to be on the bottom right, because that means high test accuracy at the same time low attack effectiveness. So by varying the degree of the cross loss reduction training, we can get a line. So this blue line is our method, which as you can be seen is generally on the bottom right part, which is what we like. And so sometimes we find that we actually get better accuracy than comparing with no defense, which is a vertical line. So this might be because the data set we are using in the training is relatively small. So by doing this, there's some regularization effect to improve accuracy. Compared with other defenses, so I think the Selena is really similar to our defending idea, but one of the main differences is it will have a higher cost because you need to remember many models and then in this retraining process. So our approach also have a significant memory cost because I think this might be using 4 virtual client because we need to remember 4 different set of parameters during training. And also there's about, I guess, 100% additional running time overhead compared with the baseline. So after we have this result, and then so we came back thinking, well, what does this really mean? So what does this missed approach really do? So the way I see it is different instances will have different degree of vulnerability to membership inference attacks. Usually, most of the instances are not vulnerable, but relatively small number of them are. And most of the existing defense do not differentiate between them. So you try to make the training kind of soft on everyone, so therefore defend against everyone, but then you are incurring the accuracy loss. So what MIST is implicitly trying to identify the vulnerable instance, because for the instance that are vulnerable, that stand out, the regularization step will make it kind of less fitting those instances. So then we are only suffering the training loss, the accuracy loss for the vulnerable instances. So therefore, the overall accuracy loss is less. So that's, in my kind of current understanding, that's what this training method does. So yeah, so thank you, and I'm happy to take any questions.